Hello. Within this experiment, you use what's called a spectrophotometer to record data that quantifies color. Just as one can quantify mass with kilograms, we can quantify color by measuring the frequency of visible light waves, as well as how efficient a substance can absorb light by manipulating related properties found within today's experiment. This lab is separated into two different parts, and everyone is split into groups of two, with each person completing their assigned parts. Part 1 is about using a spectrophotometer to find the maximum absorbance within a specific wavelength of a specific food coloring substance, which is given to you by our TA. You'll then measure the absorption spectrum of the dye between 400 and 700 nanometers and determine the maximum wavelength of said food coloring dye. Part 2 is then about personally creating your own mixture of food dye using Fruit Loop cereal of the same color as Part 1, and then measuring the same variables as before. After the lab, you'll construct a table of absorbance versus concentration of the Fruit Loops mixture, and plot the data in Excel where you will determine the molar extinction coefficient for your dye by analyzing the best fit line. Finally, you'll determine how much food dye is within your mixture of Fruit Loops. As per usual within any lab experiment, wear safety goggles as well as gloves, and exercise normal safety procedures. All waste will be disposed of in the non-halogenated waste container. Don't drain anything that you'll be using down the sink unless your TA approves so. With that out the way, let's start on Part 1. In Part 1, your TA will assign your group one of 4 dyes, and your job is to find the maximum wavelength of light absorbed by a given dye. You'll be using a 1:1 ethanol water mixture as a solvent to mix the dye into, as well as a blank for your spectrophotometer. You'll attain 4 different beakers labeled A through D, and you'll mix a specific amount of an ethanol water mixture with a very specific volume of dye, which can be found within your lab manual. We do this because we'll compare how different concentrations of the solution will affect different variables within Beer's law, which will be calculated in the post-lab. Be very precise in your measurements. You'll also be using different pipettes to transfer dyes, so make sure to not cross-contaminate pipettes. Make sure to mix the solutions. Next, fill a cuvette up to the line under the arrow with the ethanol water mixture, and make sure to not over or underfill it. To use a spectrophotometer, insert the blank cuvette into the hole, which will act as a reference to record color. Make sure that the arrow of the cuvette is in line with the same arrow on the spectrophotometer. Then, go to Experiment, select Calibrate, and select Spectrophotometer 1. After waiting 90 seconds for it to warm up, hit OK. Then, you are ready to use the spectrophotometer to record color. Once the spectrophotometer is all warmed up, begin with the most dilute dye sample and move towards the most concentrated sample when using the spectrophotometer. Make sure to use gloves and to not leave any fingerprints on the side of the cuvette, which will affect the absorption values. Then, in the top right, hit the play button and let it record for 10 to 15 seconds. Don't let it go for too long or too short. Record the wavelength where the absorption is the highest. For example, if the highest absorbance value is at 1.03, record the wavelength at that value. At the end of the experiment, there should be 4 similar graphs of similar shape, but all at different heights due to the dilution of the concentration. In Part 2, you'll be making your own mixture of dye using Fruit Loops of the same color as Part 1, and then repeating the same steps as before. You'll grab 10 rings of Fruit Loops of the exact same color, measure and record the mass, and then use a mortar and pestle to grind it up into a powder to pour into about 25 milliliters of DI water. Heat up the mixture until it starts to boil using a hot plate, making sure to stir up the mixture to speed up the reaction. Next, take it off the hot plate, cool it down, and add 25 milliliters of ethanol into the mixture and continue stirring for about 5 minutes. Now let the new mixture sit for 10 minutes and then filter it through filter paper to a volumetric flask. Don't let the solid within the solution go through the filter paper initially, as once all the liquid is filtered into the flask, you'll then add about 10 milliliters of ethanol water mixture to help filter the solution back into the flask. Once that is done, add the ethanol water mix until the 100 milliliter mark. Mix the solution a little bit, pour it back into a beaker, and use a spectrophotometer to measure the maximum wavelength just as in Part 1. Remember to dispose of any waste in the non-halogenated waste container. In the post-lab, you'll create an absorption versus concentration graph in Excel using data collected within Part 1. This is to measure the relationship between the two properties and see how that connects to Beer's equation using graph analysis. As you graph these datasets, the trend of best fit line, or the slope, should indicate the molar extinction coefficient, or epsilon for short. Epsilon represents how much light a given liquid can absorb, and is an intrinsic property, one that is reliant on the liquid itself for this property. It is similar to heat capacity, in which every substance has a different value, such as aluminum or gold having two separate values. To see this relationship mathematically, if we use Beer's law, where B, or the length of the cuvette, is 1 centimeter, it just simplifies to this equation. And if we rearrange the equation and solve for epsilon, we get this equation, which in turn is the slope of absorption versus concentration graph, as absorption is on the y-axis, which is over the concentration on the x-axis. That is all for this lab, and I really hope it helps. Thank you.